All right. We got to talk about something that is related to significant digits. The thing I want us to keep in mind is that significant digits are a communication tool. They never show up in math because they're not super important for making calculations and whatever, doing calculations, solving things. They're important for communicating something about your measurement that you made in the real world. Since we don't talk about stuff like that in math class, that's why it doesn't come up. Another thing that we need to pay attention to regarding measurements is that there is something called uncertainty. Uncertainty. Did I play the video? Is it going?
Yeah.
Thank you. When we were, we had the example up yesterday with the pencil and the ruler. If the pencil ended up between the lines on the ruler, we could maybe estimate another decimal place, but we were uncertain or there was room for debate and I couldn't necessarily prove it to you. Uncertainty is something that applies to the numbers here. As a general rule of thumb, whenever we measure something in the lab, the last digit is a digit that we estimated. So if you're using a graduated cylinder or a ruler or something like that, or even a thermometer with graduations on it, you want to obviously measure to, you want to measure to the smallest graduation that you're given, but then you also want to estimate one more decimal place. And so what we'll say is the last significant digit in the measurement is uncertain, meaning you might have estimated it correctly, you might have not. And we're just going to say that there's a give or take, there's a range of 1, so to speak. I don't know if I can make up an example real quick. So if I have like my ruler, and so maybe I'm measuring, here's my pencil. Okay, so if the pencil comes to here, 1, 2, 3, 5, 6 point something, I'm very certain that the first digit in my measurement should be a 6. Because I have a graduation, I have a line on the ruler to prove it. Good practice is to estimate the next digit. What do you think this digit is here based on where my dotted line is?
7. 6.
I heard 2 different answers. Right? I can't prove to someone, if we disagree, I can't necessarily prove this to you, but it's good practice just to go ahead and estimate it. And a educated, trained scientist like yourself will look at this and will understand that this digit is uncertain. There's a give or take of 0.5 or half of whatever this place value is. So if I'm gonna estimate that it's 6.7, what I'm really communicating efficiently is I'm saying I think that the true value is somewhere in this range. See how I went, so half of a tenth, right, is 5.05. So I went half of this place value here and then half of that place value above. So literally by just writing this, you're communicating this. You're communicating a range. Yeah?
Yes.
Kind of makes sense? And that's just the nature of making measurements in the real world. They're not entirely perfect. So if I write down 3.75 milliliters, what I really mean is a range where I go half of this place value below, 745, right? We can think of this as like 50. So 45 or up to 55. Okay, so this measurement implies a range. I'm confident in the first 2 significant digits, but the last significant digit has some uncertainty to it. It could be bigger or smaller. This applies in scientific notation as well. You guys see that? Where's the uncertainty in 150 meters? What place value is uncertain? Is it the 1, the 5, or the 0? Where's my last significant digit?
It's the 5.
Here. This is where I measured to. I measured to the tens place. So notice how far my range is. Half of a tens place, which is give or take 5. So this is not 149 to 151. It's 145 to 155 because my uncertainty is there. The last significant digit. Make sense?
Yes.
Questions? Okay, so that's all nice and good and well. This has implications for when we do calculations. All right, for those of you with a calculator, we might do some math here, so if we want to pass around the box, you want to just take a calculator or not, and just pass the box. Simple calculation. Find the area of this rectangle. Simple calculation. I assume we can all calculate area?
No. Hopefully.
If not, ask your neighbor. Just punch it in your calculator and then someone tell me what your calculator says. If you got the wrong answer, don't tell me that one. If you get the right answer, tell me that one.
6.337.
Keep going.
That's it.
Cool. Now, when we're thinking about significant digits and exactness in a measurement, this seems like a pretty precise result. I think I know the area of this box down to the thousandth place. It's pretty good. There's a problem though.
You do the other one first.
My length here was measured very exactly, down to 10,000th of a meter.
So we.
Tenth of a millimeter, yeah?
Will we just add a 0?
Maybe. Let's talk about this. Let's look into it, okay? This is very precise. This, on the other hand, not. Let's talk about the range of these measurements. We just talked about uncertainty. How much wiggle room is implied? How much range of uncertainty is in the top measurement?
Not very much.
Half of a 10,000th, right? Give or take. So not much. Do I have it up here? So my range that's communicated by this number is pretty small. So I can think of this as being like the number 80 kind of tagged on here, 75 to 85. Very precise. This, on the other hand, much less exact. Give or take half of a ones place. So 0.5 in either direction. So then that raises the question, so if I want to think about this, so this length, I have a box drawn here, but maybe I just drew this diagram based on my measurements. But the way I should really be thinking about this is I could be a little over or I could be a little under. So there's this much wiggle room in the length there. Right, my measurement's not perfect. But here, I've got like that much wiggle room in terms of the height of the box. Now, when I multiply these two numbers together, I get that number, but wouldn't there also be some uncertainty or some wiggle room in my result based on the wiggle room and uncertainty of my individual measurements? Yeah. So how do we account for that? That is a good question. Our area is going to also have some wiggle room. The area has a range of possible values, and so the way we write this needs to be reflected. Okay. Yeah, because my area could be this small number times this small number, or it could be all the way up to the bigger number multiplied by the bigger number. So whatever those two products are is kind of my range there. And so my point is I don't actually have 6 significant digits there. Your calculator does not understand significant digits. Your calculator understands math, kind of, but it doesn't know how to round it appropriately. This is where you get to be smarter than your calculator. For once. No, I'm kidding. Okay, so you have to think more than your calculator is thinking. So there are rules, there's principles that we're going to go here. So how many significant digits are in this measurement?
2.
How many in the top one? 6, right? So here's the rule for when I'm multiplying or dividing measurements. When I combine 2 different measurements with 2 different levels of exactness, my result can only be as precise as the least precise one, right? Chain is only as strong as the weakest link. If I have all this uncertainty here, well, that uncertainty goes into my result. So what I need to do is I need to round this to the same number of significant digits as my least precise measurement. Not the same place value, not the ones place, but I need to rewrite this number so that there are 2 significant digits. Where's the second significant digit? Where's the second one? It's the second 4. I need to round to that place. 456.337 rounds to what in the tens place?
150.
The 6 rounds it up. That is my result. I can be very, very confident that this is a 4 and that's a 5. I don't actually know that that's a 6. I don't actually know that that's 337. It could be a bigger or smaller number because of the wiggle room in my measurements. I can only be confident in those digits. And so it would be irresponsible, or dare I say, fraudulent, to report digits that you don't actually know. Just because your calculator spat it out doesn't mean that's what's really happening in the physical world. Okay? So the rule for multiplication and division is that my result is rounded to the same number of significant digits as the least precise measurement in the calculation. Okay, I'll let you write that down. I don't like that the whole thing shows up at once. What tarnation? Ah. There we go. When I'm adding or subtracting, I follow a different rule. There's also different rules for when you take the logarithm of something and when you, I don't know, do other functions, but we're just gonna worry about the 4 basic operations. Okay, so for multiply and divide, I need to look at the least number of significant digits. If I'm adding and subtracting, I follow a slightly different rule. Yes?
So on an assessment or quiz or whatever, how would you specifically word that you wanted us to achieve? Instead of like, if you just gave us a simple area problem and we multiplied it with that could be an answer, how would you word that you want us to specifically show?
The correct significant digits?
Correct.
I can tell based on how you wrote your answer. So if I gave you the box problem on a worksheet, the answer I'm looking for is this, not this. And so when I make a key and I grade it, I will round it correctly, and you need to have it rounded the same way. If you have this, or this, Okay, maybe there's some rounding differences, but I guess the short way of saying is I'm gonna count the significant digits. You need to have the same number of significant digits as I got based on what numbers I gave you, what measurements I gave you. Okay, we're counting significant digits for multiplication and division. For adding and subtracting, we're looking at the place value. We round to the same place value as the least precise measurement. Let's write this down, and then I'll do a couple examples, and we'll call it a day. We'll practice this tomorrow. Although we have a ton of time, so I'll give you a worksheet. So that's the result we talked about from the last slide. I will be grading you on your ability to do this, to round correctly. Yes, maybe you can do math and get the right number. Great, you'll get some points for that. But then there's additional points that you need to be thinking about of what is the appropriate way to round my result so that I'm correctly communicating the exactness of my measurement. I still see people writing, so I'll wait a second. I feel like I've said K a lot less today, so I feel good. Feeling proud. Less.
Years.
Yeah, but
Yeah, yourself. Years.
You good or still right? Dang it, I don't have any examples. Should I do some examples?
Yes.
Let's do 2 examples. Okay. We did a multiplication one. I need to add examples to this. That's embarrassing. Okay, so let's say I'm doing like a displacement thing where I have water, grudge cylinder. I put something in, the water goes up. Okay, although that's kind of a bad example. Never mind. Okay, let me just make something up. 33.75 milliliters minus 26 milliliters. My calculator tells me what?
Would it be 10?
You say 8.
Is it that?
Yes.
Can I mental math?
Yes.
Great. But I have a disparity of precision, yes? Very precise, not very precise. I can only be as precise as my least precise measurement. Now, because we're adding or subtracting, I don't care about the number of sig figs, significant figures. I care about place value. What place value is this rounded to? Hundredths. This is rounded to the ones, so I need to round this to the ones, the place value. I don't care how many significant figures I end up with, I just need to round to that place value. Yeah? I need a unit. Micrograms and micrometers and micrometers. We'll pretend it's another area. Can we do this in scientific notation? My calculator tells me what? Can someone help me out?
5.4168.
Say what?
5.4168.
Times 10 to the 7? 7 or 8?
7.
Micrometer squared. So we'll pretend it's a little area, little box, tiny box. Actually, it's not tiny because it's 10 to 7. Whatever. Multiplying, dividing, subtracting, adding. What am I doing here? Multiplying. So what's my rule? Do I care about place value or the number of significant digits?
Number.
The number of significant digits. How many do I have in this measurement?
4.
Three. I guess.
It's 4.
It's 4. Trailing zeros are significant if there's a decimal place. How many here? Which one is less precise?
3.
This one. So I'm going to round this to how many?
3. 5.
1 more and we're done. Let's do a spicy one. I'll leave that there. I'll try to cram it in here. We'll pretend this is like density, so we'll do grams minus
Do the first.
Hmm.
When do we do it after the whole thing or each part?
So now I've combined our two rules, right? We've got the addition subtraction rule and the division multiplication rule. There's different ways we can do this. Probably the best way to do it is just to do the whole calculation and then write down what your calculator gives you. So if I do the whole calculation, following PEMDAS, subtract then divide, can someone tell me what the calculator says if I do the whole thing?
0.4889.
7. Wow.
Redo. Together. Ready, set, go.
We did not get the same numbers.
Oh no.
What did you get?
If you got the wrong number, don't tell me.
I got 0.48941935.
I got 0.4887741935.
I got that too.
She got it too.
It should be close to 0.5, but it sounds like you're both 0.4 something. Let's go with that number. Loud and proud, Elliot.
48877411935.
Grams per mil. So many significant digits. My calculator's lying to me. This is malfeasance. We gotta fix this. Where do I actually round it? We gotta look at each step, okay? So if I just look at this subtracting step, do I care about the number of significant digits or place value? Place value. My least precise place value is hundredths, right there. So if I were to round this to the hundredth place, that would give me 4 significant digits, and if I rounded that, I'd end up with 4 significant digits. Am I doing this right? Someone subtract this real quick.
It is 7.576.
Okay, so I would get something like that.
Yeah.
If I just subtracted, I get 7 point something something, right?
7.58
if I did my rounding. Okay. So based on this top calculation, how many significant digits do I get? 3. Now I've got to take that number and divide it by this, yes? Okay. So 3 significant digits and 3 significant digits. When I divide, I just need to round to how many significant digits? 3. So based on that second step, I get 3 significant digits. So now I need to round this to 3 significant digits.
So you just apply the rule as you go.
You just apply the rule step by step. There's probably room for debate. I think different people might have different approaches, but this is, I think, the easiest one just to get us started
So
on.
if you do subtraction, you realize that you do division.
Mm-hmm.
Yeah.
So what should my answer be written as? 3 significant digits, 489 grams per mil. Cool. Now, I will say, there's 2 things happening here. When you do the math, I would do all of it without any rounding. So please don't subtract, then round, then plug it into your calculator, then round again. If you round every step, you're gonna get a different number. It'll drift as if you keep rounding. So do all the math, spit out the big number, then go through and just count your significant digits as you go, and then round your final answer. Okay, if that makes sense. Questions? Yes.
Okay, so it's like the 0.488 whatever. If the third significant digit and that was 9, would you do like 4.490?
Yes. If this was
9.
right, it would round to this. Is that still 3 significant digits,
Yes.
or is that a problem?
No, it's good.
It is 3. Trailing 0, decimal point present, still 3. So it still works out. If it were a big number and we had like 8 million and I had to have 4 significant digits, how do I solve that problem? Scientific notation. I would have to do 8.000 times 10 to the 6 or whatever. So if you have a big number and you run into this kind of problem, you got to do scientific notation. If it's a small decimal number, it works out the same. Good question. Other questions? All right. We better stop. I put Ben to sleep, so better move on. Okay, that's all I got for today. We will practice this tomorrow.